Alveolar gas concentration refers to the concentration of an inhalational anesthetic in the alveoli of the lungs. It is a critical determinant of the depth of anesthesia because the anesthetic effect is directly related to the partial pressure of the anesthetic in the brain, which closely parallels the alveolar partial pressure due to rapid equilibration between the alveoli, blood, and brain. The alveolar concentration is influenced by several factors. These are inspired gas concentration, anesthesia uptake into the pulmonary circulation, pulmonary ventilation, and gas phenomenon like concentration in second gas effect. Let's look into them next. When an inhalational anesthetic is delivered to the lungs, it diffuses from the alveoli into the pulmonary capillary blood based on the partial pressure gradient. This is called uptake of anesthetic agents. Because of the uptake of anesthetic agents, the concentration of anesthetic remaining in the alveoli lags behind inspired concentration of anesthetics, especially during the early phase of anesthesia delivery. Over time, as blood and tissue compartments begin to saturate, the rate of uptake decreases. This allows alveolar concentration to gradually rise and approach inspired concentration, leading to equilibrium between the inspired and alveolar concentrations. The relationship between the alveolar concentration and the inspired concentration of an inhalational anesthetic is expressed as Fa by Fi ratio. The ratio provides insight into how much anesthetic is being removed from the alveoli by the blood, which is the essence of uptake. A low ratio indicates significant uptake of the anesthetic into the blood, which slows the rise in alveolar concentration relative to the inspired concentration. A high ratio signifies minimal uptake, meaning the alveolar concentration rises quickly and approaches the inspired concentration. When the ratio is 1 or when Fa equals Fi, the concentration of the anesthetic in the alveoli matches the inspired concentration. At this point, the anesthetic's partial pressure in the brain, blood, alveoli, and inspired air is equal and the anesthetic's effect begins. So, low ratio or slower rise in alveolar concentration indicates slower induction, and high ratio or faster rise in alveolar concentration indicates faster induction. We will revisit this concepts time and again as the video continues. The uptake of anesthetic into the blood depends on a lots of factors, which is explained by Fick's equation. The equation explains the rate at which a gas is transferred across a membrane, such as from the alveoli into the blood. This rate is influenced by several specific factors. One of these factors is the solubility of the anesthetic agent in the blood, which determines how easily the gas dissolves in the bloodstream. Another important factor is cardiac output, which dictates the flow of blood through the pulmonary circulation and impacts how much anesthetic can be absorbed. Finally, the concentration gradient or partial pressure difference between the alveolar gas and the venous blood drives the diffusion of the anesthetic from the alveoli into the bloodstream. The solubility of gas in a liquid is measured by Ostwald solubility coefficient. It is defined as the ratio of the volume of gas dissolved in a unit volume of liquid to the volume of gas in the gaseous phase at equilibrium, under the same temperature and pressure. The Ostwald solubility coefficient is essentially the same as the blood-gas partition coefficient, which is used to describe how an anesthetic agent distributes between blood and alveolar gas at equilibrium. Let's take an example of halothane. At equilibrium, when there is no net diffusion of halothane molecules between alveolar gas and the blood, a higher concentration of halothane remains dissolved in blood compared to in the alveolar gas. So the blood-gas partition coefficient of halothane is high, 2.4 to be more precise. It means that, at equilibrium, the concentration of halothane in the blood is 2.4 times higher than in the alveolar gas. On the other hand, a far larger number of nitrous oxide molecules remains in alveolar gas relative to the blood. So, the blood gas partition coefficient of nitrous oxide is low. The blood gas partition coefficient significantly impacts the uptake of inhalational anesthetics, the rise of alveolar concentration relative to inspired concentration, and the speed of induction of anesthesia. Let's take an example of halothane and nitrous oxide to illustrate these effects. Halothane has a blood gas partition coefficient of 2.4, which means it is highly soluble in blood. When halothane is inhaled, a significant portion of the agent dissolves into the blood rather than staying in the alveoli. This high uptake into the blood reduces the alveolar concentration, preventing it from quickly approaching inspired concentration. In other words, there is a slow rise in Fa by Fi ratio leading to slower induction. In contrast, nitrous oxide having lower blood gas partition coefficient is less soluble in blood. This results in minimal uptake, allowing alveolar concentration to rise rapidly and approach inspired concentration. The Fa to Fi ratio increases quickly, enabling faster equilibration and rapid induction of anesthesia. The graph on the left shows the relationship between blood gas partition coefficients of different inhalational agents and how they affect Fa by Fi ratio, and ultimately the speed of induction. The table on the right shows other partition coefficients which determine the relative solubility between different tissue groups. For instance, the brain blood partition coefficient reflects the solubility of an inhalational anesthetic in brain tissue relative to blood. It determines how easily the anesthetic transfers from blood into the brain, where it exerts its effects. The rate of blood flow through the lungs is determined by cardiac output. The right ventricle pumps deoxygenated blood into the pulmonary artery, which delivers it to the lungs. In the lungs, a network of capillary vessels surrounding the alveoli facilitates gas exchange, including the uptake of anesthetics. The anesthetic is then carried in oxygenated blood via the pulmonary vein to the left atrium, and subsequently pumped by the left ventricle into systemic circulation. Cardiac output is therefore responsible for pulmonary blood flow, which governs anesthetic uptake, as well as systemic blood flow, which distributes the anesthetic to peripheral tissues, including the brain. Increased cardiac output appears to enhance the delivery of anesthetic to the brain via systemic circulation, therefore increasing the speed of induction. However, it also increases the uptake of anesthetic from the alveoli into the blood, thereby reducing the alveolar partial pressure. Since the difference in anesthetic pressure between the alveoli, blood and brain is the primary factor that drives its diffusion, the anesthetic will enter the brain more quickly when alveolar pressure is high regardless of the brain's blood flow as long as the gradient exists. So the effect of increased cardiac output on uptake takes precedence over blood flow to the brain, leading to slower onset of anesthetics. The effect of increased cardiac output is particularly pronounced for highly soluble anesthetics, such as halothane. Ventilation also plays a role in this process, but we will discuss its effects in detail later. With reduced cardiac output, less anesthetic is taken up by the blood, causing the alveolar partial pressure to rise more quickly. This results in faster equilibration between the alveoli and the brain, leading to a quicker onset of anesthesia. However, if blood flow to the brain is also significantly reduced, it can counteract the rapid rise in alveolar partial pressure by limiting the actual delivery of anesthetic to the brain. Ultimately, the balance between reduced systemic blood flow and the faster rise in alveolar partial pressure determines the onset of anesthesia, with the latter effect typically being more dominant. Both during increased and reduced cardiac output, there is a feedback mechanism that helps regulate the uptake of anesthetic to maintain a balance in the rate of delivery to the brain. With higher cardiac output, at the start of anesthesia, there is an increase in uptake of the anesthetic into the pulmonary circulation. As the anesthetic is absorbed rapidly, it lowers the alveolar partial pressure since the blood is quickly carrying the anesthetic away. This reduces the concentration gradient between the alveoli and the blood, slowing the rate at which the anesthetic moves from the alveoli to the blood and the brain. This feedback mechanism works to slow down further uptake of the anesthetic, allowing the alveolar partial pressure to rise as more anesthetics are delivered from inspired gas. With reduced cardiac output, less blood flows through the lungs, meaning the uptake of anesthetic into the bloodstream is slower. Because less anesthetic is absorbed by the blood, the alveolar partial pressure increases more rapidly with inspired gas. This increases the concentration gradient between the alveoli and the blood, which speeds up the transfer of anesthetic from the alveoli to the blood and to the brain. Another important factor determining the uptake of anesthetics is the alveolar to venous partial pressure gradient of an anesthetics. Let's understand what these pressures are. With the delivery of anesthetics, the inspired gas containing anesthetics enters the alveoli of the lung. The concentration of anesthetic in the alveoli determines the alveolar partial pressure, which drives the diffusion of the anesthetic into the pulmonary capillaries. The anesthetics then passes via pulmonary vein into the left side of the heart, which pumps it into the systemic arterial circulation. The dissolved anesthetics in the systemic arteries exerts a pressure. This pressure is called arterial partial pressure, which in our case is the systemic arteries and not pulmonary artery. The arteries distribute the anesthetics throughout the body, including the brain. Based on the partial pressure gradient with the brain, the anesthetics diffuse into the brain. With this diffusion, the brain also has its own anesthetic partial pressure of anesthetics. After the uptake by the brain, the anesthetic is returned back to the right atrium via the systemic vein. The systemic vein also contains anesthetic and has a pressure called venous partial pressure. This is the one we are interested in when we talk about alveolar to venous pressure gradient, as it is the end point of anesthetics passage through our body. The partial pressure difference between them drives the anesthetics. A high PA to PV gradient indicates a large difference between the alveolar partial pressure and the venous partial pressure, which occurs early in anesthesia when venous blood has little anesthetic. This creates a strong driving force, leading to rapid uptake of the anesthetic into the blood and rapid induction if the anesthetics is not highly soluble. As anesthesia progresses, the PA to PV gradient decreases because venous blood returning to the lungs becomes more saturated with anesthetic. A low PA to PV gradient reduces the driving force, slowing the uptake into the blood. During the maintenance phase, the PA to PV gradient further narrows and finally equilibrates as the blood and tissues are saturated with anesthetics. During recovery from anesthesia, as the anesthetic delivery stops or decreases, the alveolar partial pressure drops. At the same time, the anesthetic released from saturated tissues increases the venous partial pressure, thereby reversing the gradient. The reverse gradient drives back the gas from the brain back into the alveoli for exhalation. Though there are factors that affects this gradient like solubility and tissue uptake, the main point is that higher gradient facilitates rapid uptake and faster induction of anesthesia. Now that we are done with uptake as a factor affecting alveolar gas concentration, let's move on to how ventilation affects alveolar gas concentration. Ventilation directly affects the alveolar gas concentration of an inhalational agent by regulating how quickly fresh anesthetic is delivered to the alveoli. Increased alveolar ventilation delivers fresh anesthetic to the alveoli more rapidly, increasing alveolar partial pressure and speeding up equilibration with the blood. This results in a faster rise in alveolar concentration and quicker induction of anesthesia. Decreased alveolar ventilation slows the delivery of fresh anesthetic to the alveoli and reduces the removal of expired anesthetic. As a result, there is a slower rise in alveolar concentration, delaying the induction of anesthesia. We also need to consider functional residual capacity, which is the volume of air remaining in the lungs after normal exhalation. A larger FRC acts as a reservoir, diluting the incoming anesthetic gas, which slows the rise of alveolar concentration, delaying induction. This effect is more pronounced when alveolar ventilation is low relative to FRC, as less fresh anesthetic is delivered to the alveoli per breath. In contrast, a smaller FRC allows the anesthetic gas to achieve higher alveolar concentrations more quickly, speeding up induction. The concentration effect and the second gas effect are phenomena observed during the administration of inhalational anesthetic agents, particularly nitrous oxide, which affect the alveolar concentration of all other gases in the gas mixture. First, we need to understand what the concentration effect is, to comprehend the second gas effect. The phenomenon by which the rise in the alveolar partial pressure of nitrous oxide is disproportionately rapid when it is administered at a higher concentration is called the concentration effect. During normal respiration, the gas exchange between the alveoli and the pulmonary capillary blood involves gases like oxygen and carbon dioxide. Oxygen diffuses into the blood, and carbon dioxide diffuses back into the alveoli. However, the bulk of the gas we breathe from air contains nitrogen, which is responsible for maintaining alveolar volume. The partial pressure of nitrogen in the alveoli and the blood is in equilibrium, so minimal exchange occurs between them. Now let us see what happens when a high concentration of nitrous oxide is delivered in the fresh gas. Nitrous oxide is about 30 times more soluble than air or nitrogen. Due to its higher solubility, it diffuses rapidly from the alveoli into the pulmonary capillaries. The fast diffusion of nitrous oxide reduces the volume of gas in the alveoli, which increases the other gases remaining in the alveoli. This is the concentration effect. Furthermore, as the influx of a high concentration of nitrous oxide from fresh gas replaces the lost volume, the concentration of nitrous oxide in the alveoli increases again. With this, nitrous oxide continues to diffuse into the blood, and the concentration effect occurs repeatedly, resembling a positive feedback loop. This process, whereby the inflow of nitrous oxide replaces the lost alveolar volume, further amplifying the concentration effect, is called augmented gas inflow. To clearly understand the concept, let's illustrate it with an example. Suppose a patient's lung capacity is 4 liters. The patient inhales a mixture of 2 liters of nitrous oxide and 2 liters of oxygen, with each gas contributing 50% of the mixture. Since nitrous oxide diffuses much faster than oxygen, half its volume or about 1 liter rapidly diffuses into the blood, leaving only 1 liter of nitrous oxide in the alveoli. We would expect that the concentration of nitrous oxide to be 25% as half of it has diffused from the alveoli. But, since the initial alveolar volume of 4 liters is reduced to 3 liters, the new concentration of nitrous oxide in the alveoli is 1/3 of 3 liters or approximately 33%. This is the first phase of the concentration effect, referred to as the concentrating effect, where nitrous oxide concentration increases even after it has rapidly diffused. Now the reduction in alveolar volume by 1 liter creates subatmospheric pressure in the alveoli, prompting the patient to inhale an additional 1 liter of the gas mixture containing 50% nitrous oxide and 50% oxygen, that is 500 milliliters of each gas. With this additional inhalation, the total alveolar volume returns to 4 liters, now comprising 1.5 liters of nitrous oxide and 2.5 liters of oxygen. The new concentration of nitrous oxide in the alveoli is 1.5 by 4 or approximately 37.5%. This is the second phase of the concentration effect, known as the augmented gas inflow effect or ventilation effect. This process will occur only during the initial phase of nitrous oxide administration. Once steady-state levels are reached in the alveoli and bloodstream, these effects diminish. The second gas effect is not a different concept from the concentration effect. It is a special case of the concentration effect and applies to the administration of a potent anesthetic with nitrous oxide, where the rapid uptake of nitrous oxide enhances the uptake of a second inhaled gas. This effect is clinically significant in accelerating the induction of anesthesia when nitrous oxide is co-administered with another anesthetic agent. We will use the same illustration to explain the second gas effect by adding isoflurane so that the inhalation mixture consists of 1% isoflurane, 49% oxygen, and 50% nitrous oxide. A 4-liter volume is inhaled by the patient and contains 40 milliliters of isoflurane, 1960 milliliters of oxygen, and 2000 milliliters of nitrous oxide. As half of the nitrous oxide diffuses quickly into the blood, the alveolar volume reduces to 3000 milliliters. The new alveolar concentration of isoflurane is now 40 divided by 3000, or 1.33%. The concentration of nitrous oxide doesn't reduce by half and is now 33.3%, and like isoflurane, the oxygen concentration increases to 65.3%. As we can see, the concentration of the second gas, isoflurane, increases. This is the concentration effect. Due to the subatmospheric pressure created in the alveoli, a further 1 liter of the gas mixture is inhaled during the second breath, which contains 10 milliliters of isoflurane, 490 milliliters of oxygen, and 500 milliliters of nitrous oxide. Therefore, the new alveolar concentration of isoflurane is 1.25%. This is the augmented gas inflow part, where despite administering 1% isoflurane, the concentration of isoflurane in the alveoli is more than 1%. The second gas effect increases the partial pressure of anesthetics in the alveoli, increasing the FA/FI ratio and accelerating the speed of induction. Not everything is good about nitrous oxide, especially during the recovery phase when its administration is stopped. As nitrous oxide is discontinued, a large concentration of the gas diffuses back into the alveoli from the blood opposite to what has happened during induction. This diffusion can dilute the inspired oxygen concentration, potentially leading to hypoxia. It can also dilute the inspired carbon dioxide concentration, causing a decrease in arterial carbon dioxide levels and a subsequent reduction in respiratory drive. These risks persist for only the first 3 to 5 minutes after discontinuing nitrous oxide. Therefore, initiating recovery with 100% oxygen inhalation is appropriate.